Hello, this is Carter Stanfield. Today I'd like to talk about HFO refrigerants, or what's up with those funky numbers. First, what exactly is an HFO? The H stands for hydrogen, the F stands for fluorine, and the O stands for olefin? What exactly is an olefin? An olefin is a hydrocarbon molecule containing a double bond between two of the carbon atoms. Here are two different HFO refrigerants, both based on the olefin propene. Note that they each have a double bond between the two end hydrocarbons. Olefins form oily substances when reacting with halides such as chlorine or bromine. The word olefin comes from the French gaz olefiant, meaning oil-forming gas. French chemist Pierre-Eugène Marcellin Berthelot coined the word around 1860 from the Latin oleum, meaning oil. Chemists have developed a more systematic approach to naming hydrocarbon compounds. Alkanes are hydrocarbons with only single bonds. They are the garden variety hydrocarbons that we are all familiar with, like methane, propane, and butane. Alkenes have a double bond between two carbons, as shown here with ethene. Alkynes have a triple bond between two carbons. You've probably worked with ethine, otherwise known as acetylene. I don't like just memorizing terms without any idea where they came from. I had to know where the names alkane, alkene, and alkyne came from. On a page from Yale Chemistry 125, Freshman Organic Chemistry, I found the answer. You can get it also using this QR code. Here it is in a nutshell. In the early days of organic chemistry, people were coining names for different hydrocarbons which included a healthy dose of Greek suffixes. Unfortunately, there was not really much of a system and often multiple names for the same thing. In 1866, chemist August Wilhelm Hofmann suggested nomenclature using the sequence of vowels A, E, I, O, U to create Greek suffixes for hydrocarbon compounds. Thus we have ane, ene, eine, or eine as in Y-N-E. Although he also proposed one and une, they didn't catch on. Al is Greek for of or relating to, so putting them together you get alkanes, alkenes, and alkynes. Examples of olefins include ethene, propene, and butene. Note that each has a carbon-to-carbon double bond and two fewer hydrogen atoms than their alkane cousins. However, I don't want to confuse you with all the talk about hydrocarbons. While HFOs are built by chemically altering hydrocarbons, there are no hydrocarbons in HFO refrigerants, no propane, no butane, or any other hydrocarbon. While hydrocarbons are the base molecules which fluorinated refrigerants are made from, the resulting compounds have their own unique chemical and physical properties. The same can be said for common refrigerants such as R22 or 410A. HFO refrigerants are made by taking an olefin and replacing some of the hydrogen atoms with fluorine atoms while leaving at least one hydrogen atom. For example, the olefin propene becomes the HFO 1234YF by replacing four hydrogen atoms with fluorine atoms. HFO refrigerants contain the same chemicals as HFC refrigerants, hydrogen, fluorine, and carbon. However, they are different from HFC refrigerants in that HFOs have at least one double bond between two carbons. The most common HFO refrigerant is R1234YF. One of the things many people find confusing about HFOs is a somewhat complex numbering system. Let's dig into that a little bit. The first number indicates the number of double bonds in the molecule. Presently, I'm not aware of any HFO refrigerants that use more than one double bond, so we'll start with a 1. The second number indicates the number of carbon atoms minus 1. So in this case, the molecule has 3 carbon atoms. This makes the second number a 2, 3 minus 1. The third number indicates the number of hydrogen atoms plus 1. So in our case, we have 2 hydrogen atoms, making the number 3, 2 plus 1. The fourth number indicates the number of fluorine atoms. In our case, that would be 4 fluorine atoms. The letters describe how the molecule is constructed. I will discuss them in detail in subsequent slides. The first lowercase letter designates the atoms connected to the middle carbon. The second lowercase letter designates the atoms on the end of the molecule with the double bond. And finally, the uppercase letter on the end describes the arrangement of the hydrogen atoms. The first lowercase letter indicates the atom bonded to the middle carbon. X for chlorine, Y for fluorine, and Z for hydrogen. In this case, the middle atom is hydrogen, so the first lowercase letter is Z. The second lowercase letter indicates the atoms on the end carbon with the double bond. This is a bit more complicated because there are 2 atoms on the end and 6 possible arrangements of chlorine, fluorine, and hydrogen. So there are 6 possible letters, A through F. In this case, we have 1 hydrogen and 1 fluorine, so the letter is E. And finally, some HFOs have an uppercase letter in parentheses on the end. Not all HFOs have this. This letter indicates the hydrogen atom arrangement on the end. An uppercase Z if both hydrogens are on the same side of the double bond, and an uppercase E if the 2 hydrogens are on opposite sides of the double bond. In this case, the 2 hydrogens are on opposite sides of the double bond, so the uppercase letter is E. Why do we need all this? Let's take the chemical tetrafluoropropene. The name tells us that the molecule is built on a propene molecule with 4 fluorine atoms substituting for hydrogen atoms. But there are 3 different refrigerants that are built around this molecule with just different arrangements of the atoms. They are 1234YF, 1234ZEE, and 1234ZEZ. If you look at the end of each molecule where the double bond is, you see that although they have the same atoms, the atoms are arranged differently, making each a different chemical and a different refrigerant. You might wonder about the decision to use uppercase E and Z to indicate the hydrogen arrangement. I know I did. It turns out that the letters come from the German entgegen, meaning opposite, and zusammen, meaning together. There are some HFO refrigerants already in use, particularly R1234YF, which most cars use. It is an A2L, meaning that it is somewhat flammable. It is also a major component of R454B. Then we have 1234ZEZ and 1234ZEE. They are both used in chillers because they can be used as a low pressure refrigerant. They are also A2Ls, and you can see the lower flammability limit in both of them and the 1234YF. And finally, a refrigerant that you've not heard a lot about probably is R1336MZZZ. Yeah, that's a mouthful. If you'd rather, you can call it hexafluoro-2-butene. So the thing that's exciting about this is it's an A1 refrigerant. It has a global warming potential of only 2, and it's a class A1 refrigerant and has no ozone depletion potential. It has no lower flammability limit because it's not flammable. It is a low pressure refrigerant, so its main use as a refrigerant would be in chillers. Currently, it's mainly used in foam blowing applications. The chemical is hexafluoro-2-butene. You might notice that it has 3 lowercase letters in its name. That's because it's built on butene instead of propene, so there are two inner carbon atoms, so you need two lowercase letters to handle the two inner carbon atoms. Let's recap. HFO stands for hydrofluoroolefin. An olefin is a hydrocarbon with a double bond between two carbon atoms. While HFOs are built upon hydrocarbons, they contain no hydrocarbons. HFO refrigerants have their own unique physical and chemical properties. HFO refrigerants have no ozone depletion potential and very low global warming potential. HFO refrigerants in use today include 1234YF, which is found in most car air conditioners. 1234ZEE and 1234ZEZ are both used in low-pressure chillers. All three of these refrigerants have an ASHRAE 34 rating of A2L, meaning they have lower toxicity and lower flammability. They are mildly flammable. Exactly what mildly flammable means is a topic for another presentation.
Hi, this is Carter Stanfield, co-author of Fundamentals of HVACR. I hope you enjoyed this presentation. If you did, please consider buying my book. You can find it online at Fundamentals of HVACR, 4th edition, published by Pearson, authors Carter Stanfield and David Skaves.